Is there a remote clicker? Does that happen? Can we use it? Okay, and does it go forward and backwards? No. Oh, I don't have a USB. It's all right. I'll stand over here. Okay, I'm delighted to share with you some science. First, as a bit of a segue from our government section, I wanted to talk a little bit about what my life is like at the moment. And so I'm just sharing with you, I have 3 jobs. I'm the director of the Center for Astrophysics, Harvard and Smithsonian. I'm also the director of the Smithsonian Astrophysical Observatory, and I'm director of the Harvard College Observatory. They both expect me to be a full-time director, like their other directors, and then overseeing the entire Center for Astrophysics is a bit like having 2 children, and then overseeing the relationship between your 2 children as well is a bit like having an extra child. So my life at the moment is like this, mostly all sorts of things. So, you know, strategic planning, risk management, budgets. This year, budgets, trying to save budgets from being cut, bringing in more money, and personnel management. And you're welcome to ask me about all those things, probably best over a drink. And most of my life at the moment is spent trying to show the federal government and other places, when they ask us why you're useful, why we're useful. And so Jen had some nice slides. We also have similar slides for Chandra, showing the user base, which does include Texas and Florida, substantial users. We have a high-tran molecular spectroscopic database that also supports remote sensing, medicine, oenology, and quantum research, pollution monitoring. And then there are over 400 US-based companies that use our high-tran database, including ExxonMobil and Raytheon. And we have a minor planet center that's doing planetary defense, and we had to testify in Congress about the minor planet center and how awesome and useful it is, which I think went well. And then we also justifying the existence of the sub-millimeter array and the fact that we also have users all over the United States, and that includes Texas and Florida. Many red states, many blue states. You know, astronomy is basically, it's not political. We can live anywhere and do astronomy. Okay, so now in my spare time, I put that in quotes, in my spare time, which is not business hours, I'm very excited to do a tiny little bit of research. And this year it was almost non-existent, but in previous years I was able to get some done. And we're still working towards a reliable cosmic metallicity history. So for those of you who've been at these meetings before, the last couple of years, I've been presenting some work on determining metallicities. And so we have a long way to go to get reliable metallicity history. So these are a list of some of the problems. So we have different lines available at different redshifts. And that means that we have selection effects. Emission line signal noise selection criteria introduce selection effects, which can basically influence the metallicity range that you have in your sample. And because metallicity affects different lines differently, you need to understand that. Lines can be blended. That produces inaccurate metallicities, and if that's ignored, there are metallicity calibration discrepancies I'm going to talk a little bit about, and the problem with those is that they mimic or can hide evolution with redshift. And then we need to include all galaxies down to completeness limits. Like right now we're throwing away our AGN, and we're throwing away our galaxies that we think might have shocks in them because we can't derive an accurate metallicity for them, but they're galaxies, and if we want to understand the chemical history of all galaxies, we need to actually include them. And then we need to, so we have to be able to calculate metallicity in galaxies with these different power sources in order to drive a reliable cosmic metallicity history. So I'm going to talk about each of these individually. This takes a really long time, all these things to do and to get right. And so we're doing everything all at once, thanks to a fabulous group of students. And so I'm going to share some results from these students that I'm very fortunate to work with. So Phoebe is a first-year student, and she's been working on new metallicity diagnostics for low resolution spectra. So there are a bunch of, in particular, GRISM data have spectra where you've got H alpha and nitrogen 2 blended. And so we're working on how do you get metallicities for those galaxies. We don't want them missing from our samples. We want them in the samples. And so this is a diagnostic that she's derived, which is based on this line ratio, and which is sensitive to metallicity. It's also sensitive to ionization parameter, but it's a, it's not a huge range. It's better than the ones we had before. So this is very promising. And then what she's going to be doing next is to be able to use these samples that have this blended data to derive metallicities. She's using cosmic hydro simulations to then figure out how the emission line ratios, including this one, changes with redshift, how you'd expect it to change with redshift based on our expectations about metallicity evolution. Okay, metallicity calibration discrepancies. What are we doing about that? So this is what we've been doing for a long time. And this is work that's been taken on by first-year student Sophia. So Sophia's actually been doing metallicities since her undergraduate years, and so she's picked probably what I think is one of the hardest problems to do. She wants to resolve these discrepancies and then to be able to measure metallicities across multiple galaxies in a robust, reliable way. And what's interesting, so this is a mass metallicity relation, and many of you have probably seen this before. This is all calculated using Sloan, the same sample, but just different diagnostics. So from 1 to 10, these are 10 different metallicity diagnostics, and so it should be the same. We should be getting the same metallicity for all these diagnostics. The bottom two are based on empirical calibrations using the auroral line method applied to a very select sample of H2 regions. The top ones are all based on theoretical models of metallicities derived using photoionization models, and the ones in between are based on a mix of the two methods. And so there's this massive disagreement. This is in log scale, so this is really systematic. It's like you can you can estimate a galaxy's metallicity of between 0.3 solar to twice solar just based on the metallicity calibration discrepancy. It's really like it's like we don't know what we're doing. So we're trying to figure out what is going on here. And we really have to get local to do that. We want to understand the physics, what is going on. And to do that, we're taking very, very nearby H2 regions, and we're taking super high resolution spectra of these H2 regions. We're doing an integral field spectroscopy across the H2 regions. This is just the start. This is like a pilot study. Now we're going to be doing a very large sample. It's going to be about a 2-year campaign on the wide field spectrograph on the ANU 2.3 meter telescope, and then for some of the biggest H2 regions we've got Magellan. Sophia's applied and received Magellan time later this year to observe those as well. Okay, the beauty about this is that we can then measure the electron temperature variations. So Manuel Peinbert has been saying for a long time that the discrepancies in the metallicity diagnostics are due to electron temperature variations, and that impacts the auroral line method, might impact the strong line methods as well. And we can see this now across the H2 regions. So the top plots show there are 3 different H2 regions across there in the columns, and then the rows are 2 different electron temperature derivations. On the top we've got oxygen 3 electron temperature, on the bottom we've got oxygen 2 electron temperature. This is an auroral O2 line, doublet, and this is an auroral oxygen 3 line. And so it's absolutely not homogeneous. So there absolutely are electron temperature variations across those H2 regions. And because these are plane parallel models, we can then consider every spaxel as consider it basically as a plane parallel model. Every spaxel is a plane parallel model. The metallicity diagnostics were calculated assuming plane parallel models. So for every spaxel, we can actually do our diagnostic calculations using the auroral method and the strong line method, and then we can compare. So we will know what the effect of those systematic discrepancies are on the diagnostics. Yeah. Say again? You mean up here? Yeah. Sorry. Yeah, it's a bit blurry, isn't it? So it depends. So this scale is different from the H2 region to H2 region, but this one goes from 5,000 to 12,000. That's 5,000 to, it goes up to about 20,000. Yeah. About 8,000. Yeah. Okay, so we can then compare the temperatures in the high ionization zone, the O3 zone, and in the O2 zone, the low ionization zone. This is really interesting. So there's actually really a lot of variation, particularly in the O2 temperatures. There's some variation also in the O3 temperatures. The average temperatures agree for those H2 regions, for those 3 H2 regions. We'd need a larger sample to know whether that holds for more H2 regions, but I think it's interesting. And then we can look at those electron temperature fluctuations, so the differences between the O3 zone and the O2 zone, and for sure there are variations across the H2 region. So this is going to be impacting our diagnostics, and then we can calculate what that effect is. And you can see, so this is the direct method, the auroral method metallicity minus the strong line metallicity. If they agree, they should all be horizontal along this 0 line, right? They are really not. So there's a strong correlation here between the temperature fluctuations and the difference between the auroral method and the strong line method. This is the first time that we've been able to prove this. Okay, we thought this was the case for a long time, but not sure whether this is actually happening or not. And there's been disagreement as to how big the impact of the auroral line fluctuations is on these metallicity diagnostics. So this is where we're up to. Sophia's just finished writing up the paper, submitting to APJ this week, and so next step is to then calculate what the impact is and take it into account. We're going to have to derive new diagnostics that take into account the temperature fluctuations for both the auroral lines. It also impacts some of the strong lines. So keep an eye out for Sophia's paper on that. Okay, so next, we need metallicity calibrations for star-forming galaxies, AGN, and galaxies dominated by shocks. And we've got Pei Xin, who is a fabulous student at Harvard, and she's been working on this. So Pei Xin is producing like paper after paper of fabulous work. So I encourage you to go and read all her papers. They're all great. This is a paper which she wrote on the impact of the EPIC, which is a way of characterizing the AGN spectrum, includes the big blue bump, and on photoionization models. So these are models that she's been producing, and they're available, and she's available for collaborations on these AGN grids. And they match the UV observations. So we have new UV diagnostics that you can use and apply them to your James Webb data if you want to. And they produce nice agreement with the data that we see, which was nice. So when we make models, we don't go back and rerun the models and try to make them fit the data. Okay, so we just run the models. If they fit, they fit. They don't, they don't. It's all published in the paper, nasty or not. So this was really nice. And okay, optical metallicity diagnostics. So now with the new AGN models, Pei Xin has produced metallicity diagnostics for AGN. And so if you know that you've got an AGN that's dominating your spectrum, then you can apply these diagnostics. And these are calculated using the same photoionization models as we've calculated our star-forming galaxy metallicity diagnostics. So you can now get metallicities for a whole sample that includes star-forming galaxies and AGN. And so you don't need to throw away your AGN when you're measuring metallicities and mass metallicity relations for galaxies. So this is really a nice self-consistent method to derive metallicities. And then you can derive all sorts of other things using the same diagnostics. So Pei Xin showed that you can measure, for example, the black hole mass. You can measure the accretion rate. You can measure the E-peak of your spectrum. And so there are a range of different diagnostics that you might find useful for depending on what your science goals are for your samples. And then finally, a very difficult question that I personally have been working on since my thesis, which was published in 2002, so now you know how old I am. So we in many galaxies we've got contamination from star formation, AGN, and shocks, and/or shocks. And for the longest time we've been trying to figure out what is the relative fraction of these in a galaxy. Can we subtract star formation shocks or AGN from the galaxy spectrum? Can we then calculate things that are like, star formation rates? Can we calculate our E-peak of our AGN? Can we do these things, shock velocities, without contamination from the other power sources? We haven't been able to do that until now. It's been really, really difficult to subtract them off the same spectrum. But we've been working on it, and we think we finally have a way. So this is a 3D diagnostic diagram. This is the 2D diagram, where all the models, so H2 is red, the AGN is black, and our shock models are green and purple, depending on the shock speed. And you can see they're all degenerate, right? So the shock models lie everywhere, and then the AGN models and starburst models separate for local galaxies, but not for higher redshift or for low metallicity galaxies. You use integral field data, and I'm going to see if I can run this again. If you use integral field data, and so you have velocity dispersion on one axis, N2H alpha and O3H beta, all the models separate, and all the data lie along the models. We've got some pure shocks, so these are slow shocks without a photoionizing precursor. We've got some fast shocks in there, and then you've got AGN here, star formation over here. These actually separate into two branches if you're going to look at a different angle. And so this is a really powerful method to separate out now your star formation, your AGN, and your shock spaxels. And that way you can then derive what fraction of your galaxy emission is, for whatever line you want, is from star formation, AGN, or shocks. You can subtract the power sources off that you don't want to use. You can use shock diagnostics to derive your shock parameters for the shocked spaxels, and you can use your starburst models to derive starburst parameters for the starburst spaxels, and similarly for the AGN spaxels. And so we have done that, and so this is an example. So this is a galaxy here where we've taken the H2 contribution, the AGN contribution, the fast shock contribution, and the pure shock, slow shock contribution. And so you can see big differences, right away. You can see the H2 contribution is in a ring. We also see this in the CO 2-to-1 map. The AGN contribution is in this direction, ionization cones, similar to the X-ray map. The shock contributions are in the opposite direction. Okay, so this is really interesting. And so it does show that you can actually do this separation, and then you can derive morphological features that are verifiable using other wavelengths. And great work. And there's an interactive 3D diagrams in the paper, so you can use the QR code there and go take a look. They're pretty awesome. Okay, and then finally in the last 2 minutes, some of you here last year saw this work. Almost finished it now. So in my spare time, I'm working on extragalactic archaeology. So I'm trying to figure out whether we can track back a galaxy's merger history or dynamical history from its metallicity gradient. We're using the highest spatial resolution metallicity gradients possible. There's 120 parsec resolution. We've got 4,500 spaxels. We fit illustrious simulations model to it. We then look at the illustrious simulations we've got a single galaxy match in this case, and we look at the gas phase metallicity, the stellar metallicities, we look at the star formation history, mass history, and we're looking at, in particular, how the surface mass density of star formation and metallicity actually change with time, and whether there is something that's helped trigger the different portions of the metallicity gradient. What we find in this galaxy is the outer part of the gradient, which is fairly flat, actually formed fairly recently, infall of gas and things from mergers, and the inner part of the gradient formed early on, also due to mergers, and then an intermediate gradient just happened over a long period of time just due to gas infall. Okay, so to a metallicity history of galaxies, a reliable metallicity history, we've got a long way to go. We started on this road 20 years ago. I think we're probably in the middle of the road now, and but we're getting there quickly thanks to a fabulous group of students, and look forward to sharing results with you again hopefully next year. Thank you.
Questions?
Thanks for the really nice talk, Lisa. I'm super excited to see the temperature fluctuations. Sorry, up here in the H2 regions. So I have two questions for you. One is particularly more probing. So the first one is, can you get the aurora lines for things like nitrogen, carbon, et cetera, and see whether or not the abundance discrepancies are solved for those elements as well? And then the second question is in your personal opinion, are you now convinced that it is purely temperature fluctuations and not other effects like
that's a good
density
question.
or things like that?
Yes, in some of the H2 regions we can measure the other aurora lines as well. And we're particularly looking for the nitrogen and the sulfur aurora lines too. Although in these H2 regions, this is we're going to go deeper next time because, you know, the oxygen lines popped up, but we didn't get enough signal noise in those other two aurora lines to really measure them across the whole H2 region. You know, and it's not very useful if you've only got a few spaxels of your nitrogen 2 or your sulfur 2. You can't really tell whether there are fluctuations across the H2 region. And so when we go back, particularly with our Magellan data, we're going to be looking at all of the different aurora lines for a great big nearby H2 region. As far as do I believe that temperature fluctuations are responsible wholly for all of the different offsets in the metallicity calibrations? No. I think there's a lot of other issues as well, and things like atomic data in the photoionization models can play a role. We actually updated our atomic data recently, and it brought some of the metallicity calibrations down. There are other issues like, for example, with the empirical methods where they're using a fit to the auroral lines in H2 regions. Those can depend on the sample selection effects of those H2 regions. And so we need to actually look at all these things together. What I want to do is to be able to derive the offset and take it away.
Okay, we don't have time for more questions. Let's thank Lisa again. And our next speaker is Santi Roca Fabregat.